guys, and welcome to the Handsome Medicine. So today I decided I will talk about diffusion, osmosis, osmolality. Maybe I will go through the blood and explain to you the osmolality of the blood. But I will see. I will go through and I will see if it's too long. Maybe I will not. So let's start right now. So let's talk about diffusion. Diffusion, it's very simple. It's the movement of the molecules in a solution. It can be anywhere, in the extracellular fluid, in the blood, or in the cell. It's all the same. So what makes those molecules move? They need like an energy, like a force. Like if you want to move this, I'm applying a force. Like it's called a work in physics. My muscles, it creates an energy that is transferred to this object and makes it move. That's work. Well, it's the same for the molecules in the solution. It's kind of the same. The temperature is like, let's say, the muscle that's transferred its energy and gives it to the molecules and makes them move. So that's what we call kinetic energy. Kinetic energy, that's what makes them move. As simple as that. So you will see why I'm talking about this. It's related to diffusion. So if you have this recipient and you have water molecules in it at a certain temperature, so they have all a kinetic energy inside, so they're moving. That's what I'm saying with those fancy words. So you have this one moves like this, in this direction, can move in any direction. When they collide, they transfer the energy to the other one and they slow down. And that's how it goes. But the energy is always conserved. This is the first law of energy. It's always conserved. Like you never lose energy. When you take energy from nutrients, for example, you consume energy-rich nutrients. But you don't consume the energy. You can't consume it. It's always conserved. That's the law of conservation of energy. Anyway, that was just a side note. So you have these molecules of water in this recipient. So bear with me. They move in all these directions. You have some here, some there. Let's say, for instance, you have this imaginary membrane. It doesn't exist here. This membrane doesn't exist. It is just to point out something. So you have all these molecules that move with their kinetic energy. Or we'll not talk about kinetic energy anymore. Now we'll just focus on the main stuff, the diffusion. So what's the first law of diffusion? It's very simple. Those molecules, they will go from the biggest concentration, here they have the highest concentration, to the lowest, and they will equilibrate. How does it work? It's very simple. You have more molecules here than here. So the probability that those molecules will go to this side is way higher than the probability that those ones go to this side. So if you mingle them and you give them time to mingle, you will have simply this. They will all move from all the side, one side to the other. At the end, if we had like 5 here and 3 here, we will have 4 here. They still have kinetic energy. They always move, you know? We have 4 here and 4 here. So they went from the highest concentration to the lowest. Because at equilibrium, you have 4 here and 4 here. It's just an example. Like this one could move here and this one could move back here. It's not static. Like they always move, but at the end they equilibrate from the highest concentration to the lowest concentration. And that's diffusion. Explained with physics. As simple as that. Let's go on now. Now I will talk about osmosis. Osmosis, they say, like when I was studying medicine, they always say that water goes from the highest concentrated solution where there is the highest concentration of solutes, and never liked this definition. It was confusing me so much. Then I studied like more chemistry. I studied chemistry and physics and medicine to understand this, because I couldn't understand it. And I found a better definition. Like, it goes from the side where there is the highest concentration of water to the lowest concentration of water. That's how you can understand it. So let me explain now. So you have this time you have a semi-permeable membrane. So I'm doing it better this time. This semi-permeable membrane, why it is semi-permeable? Because water can go through, it can go through, but solutes like sodium, chloride, etc., proteins if you want, they can't go through. So it's semi-permeable. So let's say you have 5 molecules of water here, and here you have solutes. They're big blocks. And let's say you have like 3 molecules of water here. What would happen if there wasn't this semi-permeable membrane? Let's say we have 4. I can explain this later. 4, and here let's add 1. If there wasn't this semi-permeable membrane, everything would mingle. You will have 2 here, 2 solutes here, 2 solutes here, and the water molecule would equilibrate. That's what would happen. But these solutes, they displace the water, and they lower their concentration. And what did I say about diffusion? They diffuse from the highest concentration to the lowest concentration. Here you can understand it like this. The molecules of water, they bump into those big solutes. So the probability for them to go to this side is lowest. And the probability for this molecule to go to this side is highest. So because of this probability, you have more water that goes to this side until it equilibrates the concentration of water. So this is osmosis. Osmotic pressure would be like applying here a pressure, like you have 4 molecules here, 4 molecules here, and you apply a pressure, so these molecules, they don't, to restrain them to diffuse. And this is the osmotic pressure. Let me give you an example. In a tube, they always give this example of osmotic pressure. If you have a U-tube, I'm sorry for the name joke, with the semi-permeable membrane, you have a level of water here, and let's say the same level of water here. But now you add solutes, and remember this is not permeable to solutes. So you add solutes. What will happen? In this U-tube, water will be dragged from here to here. So you will lose this. And the gravitation, because the water is going up, the gravitation force will stop the osmosis to occur. That's what's happened. If you want the water, like there is a force exerted by this water to go to the other side. So if you apply the piston here and you calculate the pressure you have to apply so no water diffuses from this side to this side is the osmotic pressure. As simple as that. So now I explain to you osmosis and osmotic pressure. Solutes are in this solution osmotically active. What's osmotically active? It's very simple. If you have a semi-permeable membrane that is permeable just to water, and you put solutes or protein or anything that will not pass through this membrane, it will displace water, it will lower the concentration of water, and water will be dragged to this side. So this is what's an osmotically active particle. As simple as that. That's why when you have hemorrhages or something in the capillaries, because I talked in the introduction about the compartments of the body. If you have in the capillaries hemorrhage, you can give dextran, for example, in the blood, and the dextran, it doesn't diffuse through the capillary membrane, the endothelial cells there. It doesn't diffuse. So it drags water there. So if you have hypotension because of hemorrhage, it will drag water there and the tension will come back to normal. That's one use. There is like many uses and many diseases.